Okay, next, let's look at the ideal residence characteristics. So, first of all, let's understand that there's going to be no current flow from the AC source, unlike when we saw in a series circuit where you had maximum current flow. There will be no current flow from the AC source. Okay, so what does that really mean? Well, that you're really talking about the impedance going to zero here. So if you think about Ohm's law, you have V over the impedance, the voltage over the impedance. If this impedance is approaching infinity, you're basically going to have zero current, and that's what's going on here. The impedance is approaching infinity. So therefore, when we think of current, we think of voltage divided by that impedance. That current is going to zero. Although, if we look at the currents for both through the inductor and the current through the capacitor, those two are going to be equal in magnitude, but opposite. So this is true at resonance. Now, since this circuit, looking at this is not a simple parallel circuit, since you have a branch here that has both the resistance of the inductor and the reactance of the inductor. So what we're going to do is we're going to redraw this to create a simple parallel circuit. And the method to come up with the values is covered in detail in the book. I'll just use the values. And if you want to see how they're created, I mean, they step through it in the book. I am not going to go through all the details, because really what we're going to do is we're going to simplify this. We're going to determine some of the values that we want, and then we're going to realize there's maybe a better way to do this, and we're going to come and summarize some things that we want to work with. Okay, so what I first want to do is I want to simplify that circuit that we just had. We want to reconfigure. So let's go ahead and let me slide this over. All right. So we're going to go ahead and we want to reconfigure. Really, it's to simplify the analysis. And even at that, it's still going to be complex enough that we're going to want to make some assumptions, okay? So what we have here is, and this is really an ideal state, we're still going to have the power source, and it's still going to have a resistance associated with that. So that's all the same. All right. And then what we're going to have created a parallel resistance that represents the series resistance that we had created before, and we'll have a parallel inductance that is associated with the inductor in parallel. So that's going to be RP and XLP, and then let me move this over a little bit, and then we're going to have, of course, the capacitor associated with that. Nothing changes. So that's still going to be the capacitor that we saw before. All right, so looking at this, in terms of associating RP back to the original problem that we had, RP equals the resistance of the inductor when it was in series squared plus the reactance of the inductor squared, and that's all divided by the resistance of the inductor. Okay, and again, if you want to see how this all goes through, I mean, basically, in the other drawing, they went through and you go through the admittance, and you actually go through a conversion to create, look at a series circuit, the series branch, and convert it to parallel. So, and again, I'm going to do this, but you'll see shortly that this is still complicated enough that we need to make some assumptions to simplify everything. Okay, so the reactance that we have here is actually going to be defined by the resistance of the inductor squared plus the reactance of that inductor squared all over the reactance of the inductor. Okay, so we've created two new equations based on this simple simplified parallel circuit. And again, this thing is really, we're looking at this original circuit, except we are taking this piece here, this series branch, and creating a two parallel branches out of it. So that was the whole idea, and that's where we're headed. All right, so unfortunately I drew that red line and it's right through my drawing, but that's fine. What we really want to do now is to work this through and understand what would be the resonant frequency, and look at how we would solve some problems with this. All right, so first of all, if we were truly at resonant, then we could say, we would say what? We would say, oops, let's change that color. We would say the reactance of the capacitor is equal to the reactance of the inductor. And again, this is the inductor in parallel. This is of the new circuit that I've drawn, okay? And knowing that, then we would say that the reactance of the capacitor is also going to be equal to, well, it's going to be equal to what we had before, which was the resistance of the inductor squared plus the reactance of the inductor divided by the reactance of the inductor. So again, we're taking this here, and we're saying that is also equal to the reactance of the capacitor. Okay? All right, so knowing that, what we would do is we would solve for what is it, the resonant frequency of a parallel circuit. Okay, so like we've done before, where you set XC equal to XL and you solve for frequency, that's what we would be doing here. And you would come up with, let's see, you're going to come up with this ugly equation. And this part is familiar, but then you would also have this on it. And so that would all be multiplied by 1 minus RL squared times the capacitance over L. And this entire bracket, this is the square root, so that's to the 1/2. All right, so you have that equation. In addition, by looking at this circuit, we could see that the series resistance is in parallel with the parallel RP resistance, which is in parallel with the inductor, which is in parallel with the capacitor. So we would say our ZT is equal to RS in parallel with RP in parallel with the reactance LP in parallel with the reactance of C. All right, so looking at those two equations and understanding what we'd have to do to come up with that total reactance, I think it becomes clear that again we're dealing with something that is way too complex. Okay, so this is way too complex, and we're going to want to do some make some assumptions here and simplify stuff. All right, so that's the whole idea. All right, so let's get some space here. So we're going to move down here. So what we're going to do is we're going to look at, we're going to use this circuit, this simplified circuit that I've drawn here, to really move forward and make some approximations and solve for the frequency based on some approximations. Okay, so this is the guy that we're going to use. We're going to use a simple parallel circuit to do this. And so the first approximation we're going to say is we're we're going to assume that the Q factor for the inductor is greater than 10, okay? And that's a pretty good assumption for most cases. And actually, what we're going to do is we're going to make that assumption, and we're going to drive some of the equations that we're going to use to solve problems. But really, all the problems that you solve in your homework assignments that follow this are all going to have Q factors greater than 10. So what we're going to do here is really the important part, and understanding why we did what we did was because it was to simplify. All right, so having said all that, Q is still equal to the reactance of the inductor over that resistance. Okay, so that again is going back to those values that we defined in the original circuit. Okay, so if this is true, use the following approximations. Okay, so we're going to use these approximations. All right, so slide this up, shrink this down, and we're going to say the reactance of the parallel inductor is approximately equal to the reactance of the inductor in the original circuit. So when I say the original circuit, that's oops. The original circuit is this guy. So this right here, we're saying, is equivalent to this guy here. Okay. So this idea of using this equation that we defined is no longer necessary. We're going to say they're equivalent. So let's get back to that. All right. So those two are equivalent. What else can we say? Well, we can say, obviously, if we're dealing with a resonant circuit, we can then say that the reactance of the inductor is approximately equal to the reactance of the capacitor. And we're also going to say that the resonant frequency for the parallel circuit is approximately equivalent to what we'd have for resonant frequency of a series circuit, which is basically 1 over 2 pi square root of LC. So again, that's simplifying from where we were. So we're going to use that. And again, what we're going to do is you're going to look at a circuit, what's given, you're going to calculate your Q. If it's greater than 10, you're going to use these assumptions. Okay? All right. And I'm sorry that it's taken us so long to get to this point, but I just didn't want to throw these assumptions out there with understanding why we're using them. All right. So a couple other things here. The maximum frequency, the frequency of maximum impedance is going to be is defined as FM. So this is at maximum impedance. You're looking at frequency of being FM. So FM is really going to be equal to FM. We're going to say is approximately the resonant parallel frequency, which is approximately equal to the resonant series frequency. So again, and that we've defined right here. All right. So I'm going to redraw. Oops, let me get rid of that. I'm going to redraw our circuit with the new approximations in there. So our circuit now, well, it looks the same. All right. It is identical to what we just had, except we're going to have a better idea of what everything is equivalent to. And I'm probably not leaving myself enough room to write in here, but we're going to go with it. And I'm sorry, this is writing with a pen on a tablet is not as easy as it looks. Okay. All right. So let's scooch this thing over. I'm going to shrink a little bit. And let's go ahead and put in what we've got. So this is RS. And actually looking in this way is going to be the total impedance of the parallel circuit. So ZTP. RP here, this is RP, that is going to equal, and I'm going to zoom out a bit so I can write this in here, that is going to equal the quality factor squared multiplied by that resistance of the inductor. Okay? And then the reactance of the parallel equivalent inductor we talked about before. We're just going to say that's equal to the reactance of the inductor. And then obviously the last thing here, this is still the reactance of the capacitor. All right, so let's bring this back down, and there's what we got. Okay, so knowing that, so now we can say, so our Z total for the parallel circuit is approximately equal to the series resistor in parallel with the parallel resistor. And the reason we can say that is because we know that at resonance, the inductor reactance and the capacitor reactance are going to cancel each other. So the total impedance at this point at resonance is just going to be dependent upon the series resistor and the parallel resistor. So to continue on with this, we have the series resistor, and if we substitute the equation that we had for the parallel, we'll have the quality factor of the inductor squared multiplied by the internal resistance of the inductor. That's what that means, right? That if you go back, the RL is that internal resistance of the inductor, whereas the QL is the quality factor of that inductor. All right, so then we know that QP is going to be R over the reactance of LP, which we're going to say is approximately equal to RS parallel with, what do we got here? We've got QL squared RL. So we're using what we just defined here for our total impedance to solve for the quality factor of the parallel circuit. So this is just the inductor. Excuse me. This is just the reactance of the inductor there. All right. So to continue on with these approximations. All right. So I know this is kind of dry, but we want to get through this, and then we'll actually do some sample problems. In terms of bandwidth, so bandwidth is going to equal, obviously still equals the first or the second frequency minus the first frequency, which is equivalent to the resonant frequency over the quality factor of the parallel circuit. Okay, so those are still true. The other thing that we can define, and again, this is based on the assumption that our Q is greater than 10, is that we're going to be able to define the current through the capacitor to be approximately equal to the quality factor multiplied by the total T, the total current, okay? And then also, obviously we talked about the magnitudes of the two currents being equal, so if we're looking at the current through the inductor, it too is going to be equal to the quality factor of the inductor multiplied by the total current. All right, so those again are the magnitudes, so they're going to be equal and approximately equal to the quality factor multiplied by the total current there. All right, so just restate that we're talking for a quality factor for our inductor is greater than or equal to 10. And if we're talking about and an ideal current source, so now we're adding a new stipulation to this. If it's an ideal current source, and there will be times that we're going to define as an ideal current source, then RS, that internal resistance, is going to be equal to infinity. Or another way of thinking of that is that we're going to say RS is much greater than RP. And remember, in that circuit, we had RS and RP in parallel. Well, if RS is much, much greater than RP, then pretty much we could say that that total impedance is really going to be just dependent upon RP. It's going to be the smaller value, right? And if RS is infinity, it doesn't account for anything in the total impedance. All right, so let's move on. So what does that do for us? Well, then our total impedance for the parallel circuit is really going to be the quality factor squared times the resistance of the inductor. Okay, and again, this goes to the fact that we no longer have to deal with S. So if we go back to when we were defining when we were talking about the total impedance here, we always had RS in this, right? So we had RS, and now we're saying if RS is out of the picture, you're really only left with this piece here. So let's go back and finish up some of our approximations. What else we got? So we've got that. The last, so I think we mentioned that the Q of P is going to be approximately the Q of the inductor. Okay, so that'll be given as an inductor, and assuming if you look at it, Q is much greater, or if Q is greater than 10, then you can say that Q is also Q for the parallel circuit. And then the last piece here, and it's not going to be obvious with what we've done, but I believe they go through the details in the book of proving this out. Whereas the bandwidth, which we've defined as F2 minus F1, is also approximately going to be equal to the inductor resistance divided by 2 pi over the inductance. Okay, so that one is not something you're going to see by looking at what we've done here, but again, this is something that you can use if our Q is greater than or equal to 10. All right, moving on. What I have here is the procedure or the process to look at parallel resonant networks. Okay, so first, analysis of a parallel resonant network. Okay, so I've gotten 3 steps listed here. First, you're going to determine the resonant frequency using the resonant frequency for a series circuit. Next, you're going to calculate the quality factor for the inductor, QL, using the resonant frequency that we just determined, Fs. And then you're going to compare that to 10 to see, if that's greater than 10, then all these assumptions that we talked about we can use, and it'll be pretty straightforward. If it's less than 10, which you're not going to see, but there are a series of equations that you can use. There's a table in the book, and it will go through. Obviously, it's a lot more complicated. So typically, we look for things where the quality factor is greater than 10. So, anyways, and then the lower the quality factor is. So, for example, if you have something at say 50, that's much higher than 10. That's a more accurate solution than if you had something that was, say, 11 or 12. Okay, so knowing that, let's go ahead and take a look at a problem here. All right, this is problem 20-14. I've drawn it out here. You've got a current source that has 10 milliamps. It says the internal resistance RS is infinite. So that takes us to the case where we were looking at, we made an assumption if Q is greater than 10 and it's an ideal current source, our RS would be approaching infinity or infinity, and that's what we have. So the assumptions that we made for that, we can apply to this problem, assuming that we go through and calculate Q, and Q is greater than 10. All right, so let's go through this. We have the internal resistance of the inductor at 8 ohms. The inductance of the inductor is 4.7 millihenries. The capacitor is 0.03 microfarads. All right. The first thing we wanted to find in this problem was the frequency. Okay, the resonant frequency. So what we're going to do is we're going to use, again, the idea that we're going to calculate the equivalent series resonant frequency. All right, and that was 1 over 2 pi the square root of LC. All right, so we have all those values. We'll go ahead and plug those guys in. Square root of LC, so we've got 4.7 millihenries multiplied by I don't know what I just did, but that isn't good. Okay, let's get out of that mode. I don't know what I did. I tap on the blue points, display hands. Okay, great. All right, I don't know how I managed this, but all right, sorry about that.